Dear students, welcome back to the e-learning course 0, Basics of Finance. In session 2.1 of lesson 2, you will learn how to apply the present value formula introduced in session 1.1 for the purpose of bond valuation. There are 3 learning goals in this session. The first learning goal is that you understand how to apply the present value formula in the context of bond valuation. The second learning goal is to understand the sensitivity of bond prices to changes in interest rates. The final learning goal is to get familiar with the concept of duration and modified duration as measures of interest rate risk. Suppose now that you decide to buy a 4.25% government bond with 100 euros in face value and a maturity of 4 years. The 4.25% are the bond's coupon rate, meaning that you are entitled to an interest rate payment of 4.25% of the bond's face value each year until maturity. In our example, this means the bond pays a coupon of 4.25 euros each year. Based on these characteristics, it follows that we observe the following cash payments until maturity. 4.25 euros in the first year, 4.25 euros in the second year, 4.25 euros in the third year, and the final cash flow of 104.25 euros in the final year, which includes the repayment of the initial investment amount. The question we have to ask now is, what is the stream of cash flows worth today? To answer this question, we can apply the present value formula introduced in session 1.1 and assume that the annual interest rate is 0.15%. The present value of this stream of future cash flows turns out to be 116.34 euro. Usually, bond prices are quoted as percentage of face value. This means the price of our 4.25% government bond is 116.34% of its face value. If you have a closer look at the cash payments of the bond, you recognize that that bond pays a fixed coupon each year until maturity. This corresponds to the definition of an annuity introduced in session 1.2 and allows us to use a shortcut way to value the bond by using the annuity formula. To obtain the present value of the bond, we simply have to discount the repayment of the face value in year 4 by the corresponding discount factor, which is 1 divided by 1.0015 to the power of 4, and added to the present value of the annuity. The result, of course, is consistent with the present value formula used before and yields a bond value of 116.43. This example illustrates that the bond can be valued as the sum of an annuity and a single final payment. Another important concept in bond valuation is the yield to maturity, which is defined as the interest rate that makes the present value of a bond's cash flow payment equal to its price. You can think of this interest rate as the average rate of return that will be earned on a bond if you buy the bond now and hold it until maturity. Using the same example as before and denote the yield to maturity as y, we have to solve the present value formula for y. This is basically one equation in one unknown, and on first sight seems not to be too hard to solve. However, it turns out that you can't solve this equation by pen and paper, and you need an iterative procedure to obtain the yield to maturity. Doing so implies a yield to maturity of 0.15%. It is important to distinguish the yield to maturity from the current yield, which is defined as the coupon payment divided by the price of the bond. In our example, the current yield corresponds to 3.65%. Moreover, we also distinguish between premium and discount bonds. In the case of a premium bond, the present value of the bond's cash flow payments exceeds its face value, while for discount bonds, the opposite holds. You can also think that buying a bond for a price above face value implies a capital loss if you hold the bond until maturity, since the final payment corresponds to the bond's face value. On the opposite, A discount bond implies a capital gain, since you receive a final payment that exceeds the bond's price. Finally, for a premium bond, the yield to maturity is below the current yield, while for a discount bond, the yield to maturity is above the current yield. Now let's have a look at bonds that pay coupons at a higher frequency. An example of such bonds are US Treasuries, which pay coupons semi-annually. If we assume a coupon rate of 4.25%, it follows that the bond provides a coupon payment of 2.125% of its face value every 6 months. Since US Treasury bonds have a face value of $1,000, it follows that the cash flow stream for a 3-year bond is as follows. The coupon payments for period 1 to 5 are $21.25, and the final payment is the sum of the face value plus the corresponding coupon, which equals $1,021.25. If we assume that the annual yield to maturity is 0.965%, it follows that the corresponding semi-annual yield to maturity is 0.4825%. Discounting the stream of cash flows yields a bond value of $1,096.90. When we have a look at the data, we observe that bond yields are varying over time. This chart illustrates the development of 10-year government bond yields from the early 1960s to the present for the United States. We recognize that in the early 1980s, interest rates climbed sharply after the Federal Reserve did implement a policy of tight money to rein inflation and peaked at 15.8%. Another interesting example is related to the recent financial crisis, where a flight to quality took place in 2007-2008. During this period of high uncertainty, investors' demand for US government bonds did spike, and in turn, yields did decrease to 2.4% on an annual basis. This observation provides us with an important insight that bond yields are inversely related to bond prices, meaning that an increase in the bond price implies a decrease in its corresponding yield and vice versa. This graph shows the bond price as a function of the interest rate for a 30-year bond and a 3-year bond. We immediately recognize the inverse relationship between bond prices and interest rates, since both functions are negatively sloped. Suppose investors demand a semi-annual return of 4% on US government bonds rather than the initial 0.4825%. It follows that the price of the bond has to decline. Moreover, we observe that the bond sells exactly for its face value if the bond's annual yield is equal to the bond's coupon rate. In case the yield to maturity exceeds the coupon rate, the bond sells at a discount to its face value and vice versa. A measure used to predict the exposure of a bond to fluctuations in interest rates is duration, which was introduced by the economist Frederick Macaulay in 1938. Duration can be understood as the average time it takes to receive all the cash flows of a bond, weighted by the present value of each of the cash flows. More formally, duration can be written using the following expression, where each term corresponds to a cash flow payment. The numerator corresponds to the time-weighted present value of each payment, while the denominator corresponds to the present value of the sum of the cash flow stream. Let's have a look at an example. Suppose for that purpose a 9% 7-year Treasury bond with annual coupon payments and a face value of $1,000. This implies that the bond pays a coupon of $90 from year 1 to 6 and a final payment of $1,090 in year 7. In the first step, we need to compute the present value of each single cash flow at the current 4% interest rate. Summing up, these discounted cash flows yields the present value of the corresponding cash flow stream. The third step is to compute the ratio of each discounted cash flow to the present value of the bond. Finally, we only have to weight this fraction with the corresponding year and to sum these numbers up, which implies that the duration for this bond is 5.69 years. We just have learned how to compute duration and understand its importance. However, we are interested to obtain a measure that tells us the percentage change in bond prices to a percentage change in the yield. For this purpose, we can use modified duration, which is defined as duration divided by 1 plus the yield to maturity. Applied to our previous example, the bond's modified duration is 5.47%. This means that a 1% increase in the yield to maturity implies a 5.47% decrease in the bond price. After having carefully studied session 2.1, please start with the review questions.